Hello! Today, we're going to solve a fascinating problem in algebra known as a cyclic polynomial system. Our goal is to solve the following system of equations for all real numbers x, y, and z. Here are our three equations. Notice the pattern. The variables cycle. The first equation relates x to y, the second relates y to z, and the third relates z back to x. This cyclical nature is the key. Our main objectives are to understand the structure of this system, manipulate the equations to find a useful inequality, and then solve for x, y, and z. By the end, you'll be able to tackle similar cyclical systems. Let's begin. A common strategy for cyclic systems is to explore what happens when we assume a specific relationship between the variables. Our first objective is to analyze the structure of the system and, most importantly, identify if there's a solution where all variables are equal. Let's ask the question, what if x, y, and z are all the same value? This is a great starting point for any cyclic system, because if a solution exists where the variables are equal, it simplifies our work significantly. We just need to check if this assumption leads to a valid solution. Let's substitute y and z with x in our first equation. The equation becomes x cubed minus 9 times the quantity x squared minus 3x plus 3 equals 0. Since all equations are symmetric, if this equation holds, the others must hold as well. Now, let's rearrange this to get a standard cubic polynomial. Distributing the 9 gives us x cubed minus 9x squared plus 27x minus 27 equals 0. Does this expression look familiar to you? It's a classic algebraic identity. That's right, it's the expansion of a binomial cubed. Specifically, it's x minus 3, all cubed. So, our equation simplifies to x minus 3, all cubed, equals 0. For a number to be 0 when cubed, the number itself must be 0. This means x minus 3 must be 0, which gives us a value for x. X equals 3. This is a real number, so our assumption that x equals y equals z is valid for x equals 3. Therefore, we have found one solution to the system. X equals 3, y equals 3, and z equals 3. We've successfully completed our first objective of finding a potential solution. We've found one solution. Now we need to determine if there are any others. The symmetry of the system is a huge clue. Let's rewrite each equation by adding the 9 term to both sides. This makes it easier to work with. Our objective now is to create a useful inequality that relates the variables. We can analyze each equation on its own. Look at the right side of the first equation, the quadratic term. Consider the expression y squared minus 3y plus 3. We can complete the square to understand its behavior. We take half the middle coefficient, which is negative 3 halves, and square it to get 9 quarters. We add and subtract 9 quarters. The first 3 terms form a perfect square. This simplifies to y minus 3 halves, all squared, plus 3 quarters. This is a very powerful transformation. Why is it so powerful? Think about a squared term. The square of any real number is always greater than or equal to 0. So, y minus 3 halves, all squared, is always non-negative. This means that the entire expression is always positive. The whole term, y minus 3 halves squared plus 3 quarters, must be greater than or equal to 3 quarters, and therefore always positive. This is our key inequality. What does this mean for our system? Let's substitute this back. We now know that x cubed is equal to 9 times this positive expression. This forces x cubed to be a positive number. And if x cubed is positive, x itself must be positive. Because the system is cyclic, this logic applies to all variables. By the exact same reasoning, completing the square for z and x, we find that y cubed must be positive, so y is positive, and z cubed must be positive. So, we've achieved our second objective. We've proven that any real solution to this system must consist of 3 positive numbers. This greatly restricts the possibilities. Now we'll use a powerful tool called proof by contradiction to find any remaining solutions. Our objective is to prove that x equals sign y equals sign z is the only possible solution. Let's assume, for the sake of contradiction, that the variables are not all equal. Let's start with the assumption that x is greater than 3. We know the solution, 3, 3, 3 works. We're asking, can x be any other positive number? Let's assume x is greater than 3. If x is greater than 3, then x cubed must be greater than 27. from our first equation, x cubed equals 9 times the y expression. So, 9 times that y expression must be greater than 27. We can divide the entire inequality by 9. This gives us y squared minus 3y plus 3 is greater than 3. Subtracting 3 from both sides, we get y squared minus 3y is greater than 0. Factoring out a y, we have y times y minus 3 is greater than 0. Recall that we proved all variables must be positive. This means y is positive. For the product to be positive, y minus 3 must also be positive. If u minus 3 is positive, then y must be greater than 3. So, we've established that if x is greater than 3, then y must also be greater than 3. This is a crucial link in our chain of logic. Let's extend the logic from the previous scene. We found that if x is greater than 3, then y must also be greater than 3. Our objective here is to complete the cyclic argument. Now, let's use the second equation in our system. We know that y cubed equals 9 times the z expression. Since we just showed y is greater than 3, we know that y cubed greater than 27. This means 9 times the z expression is greater than 27. Dividing by 9, we get z squared minus 3z plus 3 is greater than 3. Subtracting 3, we have z squared minus 3z is greater than 0. Factoring this gives z times z minus 3 is greater than 0. And just like before, since z is positive, we must have z minus 3 be positive. This implies that z is greater than 3. So if x is greater than 3, then y is greater than 3, which implies z is greater than 3. Let's take this one step further. What does z is greater than 3 tell us about x? Using the third equation, we have z cubed equals 9 times the x expression. Since z is greater than 3, z cubed greater than 27, which means 9 times the x expression is greater than 27. Dividing by 9 gives x squared minus 3x plus 3 is greater than 3, which simplifies to x squared minus 3x is greater than 0. Factoring this gives x times x minus 3 is greater than 0. Again, since x is positive, we must have x minus 3 greater than 0, which means x is greater than 3. So we started with the assumption x is greater than 3, and we concluded x is greater than 3. This is what we call a cyclic argument. If one is greater than 3, they all must be. But can they actually be greater than 3? No. This creates a contradiction. If x is greater than 3, it must be greater than 3. This is like saying 5 is greater than 3 implies 5 is greater than 3, which isn't wrong, but doesn't rule anything out yet. Let's formalize the contradiction we hinted at. We've shown that if any variable is greater than 3, then all of them must be. Here's our cyclic sequence of inequalities. It means that if we are in the region where x, y, and z are all greater than 3, the equations are satisfied. The problem is, this region doesn't contain any real solutions. Let's demonstrate why. Let's consider the function f of t equals t minus 3, all cubed. As we saw in the first step, our original equation for x when y equals sine z equals sine x was f of x equals sine 0. Now let's examine what happens if t is greater than 3. For any number greater than 3, f of t will be positive. If t is greater than 3, then t minus 3 is a positive number and cubing it results in a positive number. In other words, there are no solutions to ft equals sine 0 for t is greater than 3. What does this mean for our system? Let's go back to our rewritten equations. Suppose we have a solution, x, y, z, where all variables are greater than 3. Let's look at the first equation. The right side is 9 times a square, which is at least 0, plus 27 quarters. This means that x cubed must be greater than or equal to 27 quarters, which is 6.75. This is consistent with x is greater than 3, as 3 cubed is 27. However, let's consider the relationship between x and y more closely. The function g of t equals 9 times t minus 3 halves, all squared, plus 27 quarters, represents the right side of our equation. The graph of this function is a parabola, opening upwards, with its vertex at t equals 3 divided 2. For t is greater than 3 halves, the function is strictly increasing. This means that as the value of y increases, the value of x must also increase. This confirms our cyclic argument. If x is greater than 3, then y is greater than 3, and so on. But we also know that for ft equals sine 0, which is the system's core identity, the only solution is t equals sine 3. Here's the contradiction. Our first analysis showed that x equals sign, y equals sign, z equals sign 3 is the only value where the function ft becomes 0. The cyclic argument proves that if a solution exists with x3, then all variables are forced into that region. But there are no solutions to the ft equals sign 0 equation in the region t3. Therefore, our initial assumption that x is greater than 3 must be false. This completes our proof by contradiction for this case. So, we've proven that x cannot be greater than 3. What about the other side? Could x be less than 3? Let's explore this possibility. What if x is less than 3? If x is less than 3, then x cubed must be less than 27. From our first equation, this means that 9 times the y expression must be less than 27. Dividing by 9 gives us y squared minus 3y plus 3 is less than 3. Subtracting 3, we find that y squared minus 3y is less than 0. Factoring this expression, we get y times y minus 3 is less than 0. For a product of two terms to be negative, one term must be positive and the other must be negative. Since we've already proven y must be positive, this means y minus 3 must be negative. If y minus 3 is negative, then y must be less than 3. Once again, we can apply this logic cyclically. If x is less than 3, then y must be less than 3, which in turn means z must be less than 3. This establishes our second cyclic argument. If any variable is less than 3, they all must be. But let's think about this. If z is less than 3, then z minus 3 is negative. When we substitute this into the equation, z cubed equals 9 times the x expression, we get a problem. Z cubed would be a negative number, but the right side, 9 times the x expression, we've already shown is always positive. A negative number cannot equal a positive number. This is our contradiction. We have reached a contradiction. Our initial assumption that x is less than 3 must be false. And by the same logic, y is less than 3 and z is less than 3 are also false. This fulfills our objective of finding a proof for this case. Let's summarize our journey to find the solution. Our final objective is to conclude from our findings. First, we found a potential solution by setting x, y, and z equal. This led directly to x equals sign 3, so we found the solution. 3, 3, 3. Next, we showed that any real solution must have positive values for all variables by analyzing the quadratic terms. This was our crucial first step in limiting the possibilities. Third, we used a proof by contradiction. We assumed a solution existed where x was greater than 3 and found that this led to a contradiction. Specifically, it forced z to be greater than 3, which made z cubed positive, while the expression for z cubed, which depended on the positive x term, also gave a positive result, but did not guarantee a solution to x to 3 cube above. Fourth, we used another proof by contradiction, this time assuming a solution existed where x was less than 3. This led to a logical inconsistency, where a variable's cube had to be negative, but its corresponding expression from the equation was guaranteed to be positive. This was a clear contradiction, proving that x cannot be less than 3. So, if x cannot be greater than 3, and x cannot be less than 3, what must x be? The only remaining possibility is that x must be exactly equal to 3. Since the system is cyclic, this implies that y must also be 3 and z must be 3. This proves that the only real solution to the cyclic polynomial system is the one we found at the very beginning. The unique real solution is 3, 3, 3. We have now successfully solved the system using a combination of direct calculation and elegant proof by contradiction. This demonstrates how analyzing the structure of a problem, like a cyclic system, can lead to powerful and surprising results. Great work!